Hi guys, welcome to Unit 3, talking about human population. This is video 12 on population ecology. So after watching the video, you should be able to describe ways in which population can be classified, calculate the change in the population over time, and graph exponential and logistic growth models of population growth. So populations can have different characteristics. They can be different sizes, densities, geographically distributed, sex ratios, and age structure. So we're going to talk about each one as we go through. So for these things, we're going to look at a population of rabbits. So when we talk about population size, N in statistics is always what you use for population size. So that's going to be our N. So for this situation, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 rabbits. So our N is 9. Okay, and we can change in that population size, and now we've lost 2 rabbits, so our population size is now 7. Or we could add 3, and our population will be 10. So looking at density, in this situation, we would have a low density. They're all just kind of scattered around. Or we could have a high density. They're in a much, much smaller area. And if you remember from other science classes, density is mass divided by volume. And in this case, you have number of organisms divided by an area. You can also have distribution. They can be randomly distributed, or they can be uniform, or they could even be clumped. So it might be a good idea to draw some pictures with those terms. You need to know those distribution patterns. Now, most things are going to be clumped because it is good to travel in groups. Think about a lion pride or a herd of elephants. There's safety in numbers, so it's better usually for organisms to be in clumps. We also have sex ratio. We can look at the number of male versus female. So the pink ones are female, blue ones are male. And then we could take those and put them in an age structure. So we could actually order those based on their sex and also their age. And when you do that, you get things that look like this. So down here would be the youngest age rabbits. These are the females on one side, males on the other. And as we go up in the age structure, they get a little bit older as we go. So looking at populations, we need to be able to calculate population change. Here is your formula. Now we're starting with N naught, that's your initial population. And our initial population in this situation is 10 rabbits. So we have 10 rabbits in this box. Now how do we calculate a change? Well, our formula is going to be births minus deaths. So how many individuals are born, how many individuals died, how many individuals immigrated coming in, and how many individuals emigrated, they left. Okay, so we're going to go through this and actually insert some numbers here. So you'll notice that this rabbit had 3 babies. So your births is 3. And then you'll notice that this rabbit that was right here now died. So we took 1 away. That was our deaths. So how many rabbits are going to immigrate? They're going to come in. Oh, well, we have 1 that just popped in over here. And then how many rabbits are going to immigrate? They're going to leave. And that was 2. So we had 2 rabbits over here. So our population change, our change in N, that's what this delta stands for, is 3 minus 1 plus 1 minus 2. And when you calculate that, you end up getting a change of 1. So our population change in this situation is only 1. Now we can also look at a growth rate, and we can calculate, over time, how much did this population grow. So our formula for that, growth rate is R, equals the change in population, the change in N, divided by the initial population. So you always want to go back to that initial population. Students oftentimes want to use the ending population number, and that's not what you want to do. So in this situation, we had a change of 1. So we would do this way. 1 is going to be our delta N. We had an initial population of 10. So you have 1 divided by 10, 0.1. You could also look at 10%. Any of those answers would be correct. So if a population is allowed to grow exponentially without any factors limiting it, that's something called the intrinsic growth rate. Now, no population can actually do that, though. They cannot increase in size indefinitely. But your intrinsic growth rate, which is the biotic potential, is the rate at which a population would grow if there were no limiting factors. And then carrying capacity is the max population of a species that the habitat can actually sustain. So what is the carrying capacity going to be? You will have intrinsic growth rate for a little while, and then you'll eventually reach your carrying capacity. So let's look at a few graphs for that, and I encourage you to write these graphs or draw these graphs down. So here is your biotic potential, also called a J-shaped graph. And then this orange line right here is your carrying capacity. So now we have hit the carrying capacity here. It doesn't just kind of sit right on it. It normally fluctuates up and down kind of in this curved manner. This is also what we call environmental resistance. So this might be food, water, space. All of those different things are going to be impacting that species and not allowing it to continue to grow. And once again, this is your exponential growth. That's your J-shaped curve. So here again, we have a species of deer, and they are growing at the biotic potential, growing exponentially. And then all of a sudden, though, you end up getting what we call a population overshoot. So here's carrying capacity down here. And right now, these deer have completely overshot their carrying capacity. And what that means is eventually you're going to have a crash coming down. And you do need to be able to identify this graph as well. So I would encourage you to write down that population overshoot and then the crash as well. And in this case over here, we have again sheep doing the same thing. They have overshot, and then it goes down, and now you're going to see a little bit of this wiggle room around the carrying capacity. So this is your J-shaped curve. S-shaped curve would be this one right here once you've reached that carrying capacity. So this is J-shape, exponential growth, and then S-shape is going to be the logistic growth. So make sure you know and can identify exponential versus logistic growth models. So a question for us is, can we continue to expand the Earth's carrying capacity for humans? We know right now that we have not reached the carrying capacity of humans on the Earth. Or there's a kind of more scary scenario where maybe we have, and we've done kind of this overshoot and our population could crash behind that. But most people believe that we haven't gotten that far. They think that the carrying capacity of the Earth for humans is somewhere around 10 billion, something like that. So looking at some population curves that we see, and this is kind of thinking about once we have hit that carrying capacity. So we have stable. It is kind of exactly what it sounds, slightly above and below carrying capacity right here. I would encourage you just to draw the graph. Don't really need the words if you do. Then you have eruptive, which is you're following along kind of the stable, and then all of a sudden something happens and you're able to increase your population, but then you're going to have a downfall again. So this is that reindeer scenario that we were just seeing. And you have cyclic. This is your boom and bust. So that's exactly what it sounds. It is a cycle going up and down, up and down. This is predator-prey graphs that we'll see in just a moment. And then you have irregular, which is this weird squiggly line right here, the purple one. We don't really know what's going on there. That's one of those things that maybe you can study as a scientist. We're not sure why we get that kind of population curve, but sometimes we do. So here is a cyclic or boom and bust cycle. This is predation, predator-prey graph. So you'll see that this is the hair curve, the purple, and then the lynx is kind of following roughly the hare population. Now, I think we've talked about this before, but if not, this area right here that we see, you may remember from before that this is called lag time. So please make sure you have that also. I'll write it up here for you as well. And just kind of the basic thing to understand here with the lag time is that the prey population is always going to follow the predator, or the predator population is always going to follow the prey, but it is kind of a little bit of a time lapse there before it actually happens. So again, this is a cyclic boom and bust cycle that you see. And when we look at survivorship of species over time, there's three different scenarios kind of that you can follow. So I would encourage you to actually draw this graph, label it type 3, 2, and 1. Also label it with a few animals that are up here. So humans live a long time. So what you're seeing here is the number of survivors and the time or the age that they go to. So humans typically survive as young people, as babies. They survive for a good long time, and then eventually they'll die off, at a good ripe age. Birds are kind of a constant loss, so there is just kind of a linear loss going all the way down. And then things like most insects and reptiles, things like that, there's a lot of babies that are born, but a lot of them die very, very quickly. Same thing with seeds, and you see in this acorn tree situation that there's a lot of death kind of early on. Only a few of them are going to be able to mature on to different to be mature trees. So that's early loss, constant loss, and late loss. And make sure you have examples. And then what kind of goes with that? Well, reproductive patterns go with that. So if I'm an R-selected species, something like a cockroach, most insects, most reptiles, I'm going to have a ton of offspring. That means I don't have to give a lot of care to them. Snakes, for example, they just hatch and kind of go off. These are going to be those type 3 very early lost species. So get a few of these characteristics written down. We'll talk about this in class as well. And then things like humans, elephants, big mammals are going to be K-selected. They have many fewer offspring, but those offspring tend to live much longer, and they will die off kind of later in life. And something to think about, if the Earth experienced significant warming during this century, as is projected with climate change, is this going to favor R-selected or K-selected species? So kind of think about that. We'll talk about that a little bit as well in class. And then finally, if you've ever gone deer hunting, some of you might enjoy that. In the 1920s, white-tailed deer in the U.S. were almost extinct. So there were some laws put in to protect these deer. However, now there's a ton of these deer in the US, and they're causing a lot of problems. So there's 25 to 30 million. I'm sure you've seen white-tailed deer at some point in your life. They cause a lot of vehicle collisions. There's 1.5 million per year, which poses risks to humans and also our property. They also like to transmit diseases, Lyme disease specifically. There's deer ticks, ticks that get on deer and then get on animals and also humans and transmit disease. So this is one of the reasons why we have such a big deer season in the United States, because it's really encouraged to go and shoot some of these for population control measures, if that's your thing. Okay, that's all for you. Bring in your questions tomorrow.